All right, this topic is differentials. This is very important. We're going to use this when we get to integration especially. So we will now formalize two new variables, dx and dy. So in the past, we've always seen them together as dy dx, as a fraction, and we've never separated them. Well, now we are going to actually define the variables separately with the property that when their ratio exists, it is equal to the derivative. Definition. Let y equal f of x be a differentiable function. The differential dx is an independent variable. The differential y is defined by this equation here. So the differential y is defined to be the derivative of f times the differential dx. So if I were to ask you to find dy for this equation here, what would we do? Well, it tells us dy is equal to the derivative times dx. So we got to take the derivative of this function. So let's do it. What's the derivative of x to the fifth? Hopefully you've got 5x to the fourth plus the derivative of 37x. That would be 37. Notice I'm putting this in parentheses and then putting the dx, because in the notation it's the entire derivative dx. So it's the entire derivative in parentheses dx. And that's it. That's your dy. So dy is defined to be the derivative of the function times the differential dx. Now, find the value of dy when x equals 1 and dx equals 0.2. Now, I'm going to show you geometrically what this means in a minute, but for now, let's just plug it in. So dy is equal to 5x to the fourth plus 37. And this is why the parentheses are important, because all of that is times the dx, 0.2. So if we work it out, that's 5 plus 37, so that would be 42 times 0.2, which would be 8.4. Okay, so what does this mean? Let's interpret. This says dx you need to think of as being the change in x. Change in x. So many times we use delta x to refer to that, but this is a very small change in x. If x changes just a little bit, so in other words, in this case, we're going from x equals 1, we're changing by 0.2, so x is now equal to 1.2. What impact does that have on y? Well, y has a value here, has some kind of number. The change that we see in y is going to be y plus dy. That's the change in y. So what we have found here is the corresponding change in y. But this is the change in y along the tangent line. So if I were to go to the picture here, remember f is the curve here. What we are talking about is this red tangent line right here. So we have our initial x, which in our problem was a 1, and then we moved delta x over to 1.2. So what impact did that have on our y value? Well, we had our y value right here, and then when we find dy is how much change there is along the tangent line, not along the curve. Along the curve would be delta y. That's the actual change in the function. What we have found is the change along the tangent line. So if we go from our point, we change by dx, we get to this point on the tangent line. So if I go over here, this distance here is the dy. Okay? So when we find the differential dy, we are finding an approximation for how much the function changes, but it's not the actual change in y. Remember, if this is a super duper small change in x, then the linearization and the function are approximately the same. This picture is showing you when you have a larger change in x. So 0.2 is considered a fairly large change. But they want you to see that it's not exactly the same. It's just close. So if dx was smaller, this would be a much closer tangent line to the curve than what you're seeing here. So don't think of dy as the actual change in y for the function. Think of dy as being the change along the tangent line and its approximation to the change in the function. All right, so let me read this just to make sure there's nothing else here that you might find useful. So when dx is a small change in y, the corresponding change in the linearization, the tangent line, is precisely dy. Not the change in the function, the change in the linearization or along the tangent line. Therefore, dy represents the amount the tangent line rises or falls when, depending on which direction your tangent line goes, when x changes by an amount dx. Or we can call it delta x. But remember, this has to be small. All right, this is another notation. So we did dy equals this. Instead of using y, we do occasionally use df. I don't think we'll use that in this course, but you might see it later on. All right, so we can actually find a differential for something more complicated, something more interesting. We can use the formula above, but we can actually work with this as a notation. So think of d as saying, take the derivative. So remember we used to do d dx? Well, this is take the derivative, but we're not going to do the dx on the bottom. He's going to appear in a little bit different way. So d, take the derivative. Well, to take the derivative of tangent of 2x, remember 2x is inside of tangent, we should do what rule? Chain rule. So first the derivative of the outside. What's the derivative of tangent? Secant squared. The inside stays the same. Times, I'm not going to do it. I'm going to write what I'm going to do. Remember, d is how we write in differentials, take the derivative. So we're going to take the derivative of the inside. But the 2 is just a constant, so what can we, or constant multiple, so what can we do with that? We can just take it out. So we have secant squared of 2x times 2 dx, the derivative of x. Well, that's just dx. We don't need the parentheses. That is our differential dx that we need at the end of our problem. So there you go. So what we just found here was the differential of this function here. So you can think of this as being dy, where y is tangent of 2x. And we did it by using d as an operator, rather than simply finding the derivative and putting dx at the end. All right, let me do it again. So this one's a little more interesting. Instead of chain rule, we have quotient rule. If you want to write out your u and v, go ahead, take a minute and do that. But I'm actually not going to do that. I'm going to just work it out. So quotient rule. First of all, you need the derivative of the top. Remember, d is how we say take the derivative. So I'm going to write dx, meaning take the derivative. So dx, derivative of the top times the bottom, minus, we keep the top, times the derivative of the bottom, all over the bottom squared. Okay, so what can we do to simplify? Well, d of x, I can actually put parentheses here if you want. The derivative of x is dx. That's our differential. So we're just going to leave that. So dx times the x plus 1. We can't really do anything there either. Minus x. Now here, derivative of x plus 1. We can use the distribution law to take the derivative of each term separately. So this is actually the derivative of x plus the derivative of 1. Well, the derivative of x is dx. And the derivative of 1, a constant, that goes to 0. So that's gone. You went to 0. All of this is still over x plus 1 squared. Now, to find the differential, what we want is we want the dx to be at the end. So how can we achieve that? Well, we have two terms on top, and they both have dx. So what we can do is we can factor dx out of the top. So we're left with x plus 1 minus x over x plus 1 all squared. The x's we can simplify, and there you go. So this is the same as if you had just taken the derivative and then put dx at the end. So the derivative of x over x plus 1 is 1 over x plus 1 squared dx. That dx you can put on the top or beside it, either way, but I wanted to make it obvious that this is your dy. This is the derivative of your function, dx. All right? So that's what I needed to cover for differentials. So we talked about a couple different things. We talked about the geometric interpretation, and we talked about how to find differentials. You have two techniques. Find the derivative, put dx, or you can use this concept of d being an operator, the differential operator, and work it out with the d throughout it. Either way will work. Study hard, have fun. I'll see you in the next video.